Okay, so good afternoon, good morning, good evening. My name is Michael Pesin, and I serve as a Deputy Assistant Secretary for the Office of Electricity at the United States Department of Energy. I really appreciate the opportunity today to discuss some of the current challenges and a lot of exciting opportunities that we have within the electric grid, and also share with you the critical initiatives the department is actively pursuing to modernize our nation's power system. So as I mentioned, I'm working at the Office of Electricity, and our office has a very unique and very specific mission. So we lead departments of energy research, development, and demonstration programs that are designed to strengthen and modernize our nation's power grid so that America can maintain reliable, resilient, and secure electricity delivery infrastructure. So the way we do it is by working very closely with industry and many other stakeholders, and we drive technological operational advancements that ensure that every American home and business has reliable access to affordable energy, that America sustains our global leadership in the clean energy transformation. And our portfolio of programs is focused on software, hardware, modeling, and addressing many system integration issues, as well as security policy and other cross-cutting issues across the electric grid. So all our programs are based on 4 pillars. We are ensuring that electric grid can maintain reliability, resilience, security, and affordability. So all our programs are guided by these principles to make sure that all these 4 pillars are supported and we can have electric grid supporting any changes that may come today or in the future. So as I mentioned, our office is focused on the electricity delivery system, which is the core of electric grid. It's perhaps most complex part of the electric grid and, well, subjectively, the most important part. It's more than just wires and poles. Electricity delivery system is what brings power from the sources of energy where it's produced to all the loads that it serves, but it also supports many other functions. It provides power flow management, enables situation awareness. It relies on communications, control, computing, analytics, and cybersecurity, many other challenges that are facing electric grid are addressed through managing and operating electric delivery system. So traditionally, industry calls it T&D, transmission and distribution, but as grid evolves, line between transmission and distribution getting more and more blurry. So we call it EDS, electricity delivery system, because you can no longer speak about transmission without considering distribution and vice versa. And the third component of that is energy storage that is becoming increasingly important. Because as electric transmission and distribution moves electricity in space, so electricity storage moves you electricity in time. And those are becoming more and more important as we get more and more renewables and changes happening to electric grid. So let's talk about these changes. So what is driving this change? So as you know, we have very ambitious goals to decarbonize the grid and the entire US economy. And to do that, we're putting a lot more renewable generation sources. And these generation sources are solar and wind, and they call non-dispatchable. Right? You can't really control sun and wind, so you need to find other ways to control the balance between supply and demand. The other challenge is most of these resources are different from the traditional rotating machinery, which has a heavy mass and had a lot of inertia. Those resources are inverter-based, so they don't have this inertia, so we need to find ways how to compensate for loss of this inertia to the contributor to grid stability of operations. We also see a lot of changes at the edge of the grid. Many consumers are installing solar on the rooftops and a lot of distributed generation coming online. We are experiencing more and more bidirectional power flows in distribution systems. Those systems were never intended, never designed to support these bidirectional flows. We need to change protection of the systems. We need to change the way we operate. We need to make sure that equipment supports these bidirectional power flows. So there's a lot of work need to be done there. And other challenge is really quickly evolving demand for electricity. With electrification of loads, especially electrification of transportation, the demand for electricity is not only growing, but it's changing. So we're seeing new peak demands. We're seeing a lot of new requirements for power quality. So all these needs to be addressed. Those are the technical challenges. But we're facing not only technical challenges, but many other challenges are facing electric grid. So in addition to all the transformation that we see, we have growing physical and cyber threats. And those threats can be made such as physical attacks on our infrastructure or cyber attack on energy systems by bad actors, or such things as potential EMP, electromagnetic pulse. We need to be prepared for all of this. But also natural threats are increasing. We have hurricanes with increased frequency and severity, changing climate. We have wildfires that devastate entire communities. So these are the things we need to address. We need to work on this and solve with technology policies. The other issue that we are addressing at the department is making sure that we support energy justice to reduce social inequalities. So we are at the department supporting low-income communities, disadvantaged communities, to ensure that the clean energy revolution will lift up these communities that for many years they've been left behind. And we're making sure that these communities can benefit from this energy transformation process. So energy justice is for low-income communities is something that allows them to benefit from all these new jobs, new innovation, and new technologies that are becoming available. And speaking of workforce, so as you know, we have significant shortage of skilled labor in this industry. Right now, United States unemployment is near its lowest level in 70 years. And the country labor pool is already stretched thin. But the workforce in this industry is especially thin. So we need to train new workforce, both in academia and skilled labor, to make sure that we can have a support for this industry today and for years to come. And last, but definitely not least, is globalization of supply chain. So this challenge is becoming very, very in post-COVID, post-pandemic world, we see significantly increased lead times for equipment, many components. It's especially bad situation with transformers. So right now, the transformer lead times are some 4 to 5 times, sometimes 6 times longer than it used to be before pandemic. So we are working with the industry on addressing this challenge, trying to identify what are the ways to support or create domestic manufacturing, domestic supply chains, how to reduce production time, how to make transformers more uniform, more universal, so they're not one of the kind designed for each specific application. So those are some of the things that we're doing to address these challenges. But the grid itself needs to really change. So the expectations for the grid are changing. So historically, we had very simple requirement for electric grid. We needed this grid to provide affordable power, reliable power, and secure power. So as long as your lights stayed on, everybody was happy. But now we have different emerging expectations. We need to integrate a very diverse set of generation resources. We also need to maximize benefits of end-use efficiency and storage. So electrification of transportation sector to reduce dependence on imported oil puts additional electric grid. And we also need to meet environmental constraints. That causes fundamental changes how electric grid is designed, planned, and operated. So historically, you had a lot of rotational inertia from these heavy machines that produced electricity. You were able to dispatch generation to match your load at any given moment of time. And your loads were pretty passive, predictable, and your entire T&D infrastructure was static. So what it allowed you to do for grid operations, you can have operator-based grid management. So people were able to control the grid in real time. Most of the controls were centralized. We had SCADA measurements that got updated every 2 to 4 seconds. And we were able to do some offline analysis that would provide us limit settings, whether it's for line ratings or for protection. But emerging grid is different. The stability is reduced. We have much faster dynamics. The generation becoming stochastic. Consumers becoming more engaged. And TD infrastructure is becoming really adaptive, flexible. So that requires us to have very different paradigm for electric grid. We need to have more flexible and resilient systems. We have to have multi-level coordination and very precise control. there is a growing requirement for much better observability and situational awareness. So we need to have advanced sensors and data acquisition, and we need to have high-speed, advanced, and robust, very secure communications. And our analytics needs to be lightning fast. It needs to be faster than real time, so we can predict what can be happening with the grid. So it requires new tools such as artificial intelligence and machine learning. So what are the key changes that we need to enable this? So starting from hardware, we need to have new systems and components. And we are working on modular sustainable systems and components with very fast dynamics. A lot of effort is put in power electronics because we are developing new components that can be fully controlled and can be more flexible, and power electronics is perfect for that. System operations need to have a real-time situational awareness, analytics control, and it needs to be able to coordinate under varying system conditions, different configurations, and also different market schemes. Planning analysis, we need to have modeling, simulation, analytical tools to support holistic planning and system design with different scenarios, options, and architectures. And institutional decision-making needs to change. We need to make sure that we align policies with customer expectations and grid investment strategies, so they can bridge the gap between technology development and technology adoption. So where the grid is going? So this is a very interesting question. Nobody has a crystal ball, but there is a number of discussions about what the future of the grid looks like. So today we have this very capital intensive, very tightly coupled electric grid. One of the trajectories that the grid is developing is with a lot of generation, renewable generation on bulk system connected transmission, requires high voltage AC and DC grids with a lot of storage to support intermittency. But the other trajectory is puts a lot of distributed energy resources with complex industry structure on the consumer side, on the distribution side. And that creates this very capitally diffuse grid that is very difficult to manage, but it's a different direction. So the future grid is not one or another, it's both. So we need to balance between supporting large bulk systems that we need to improve and force, and we need to be able to support all these new distributed resources, new types of operation, new markets. So we really need to have dynamic and coordinating grid across both transmission distribution, but also customers. So we can't do just separate planning for transmission distribution and your loads. It all needs to be coordinated. So the grid ultimately needs to evolve from the system that we have today. It is more similar to highway. So the grid system that is similar to internet. It's flexible, so we can control all flexible generation loads. We can have a lot of energy storage. We need to have some replacement for inertia. We need to have multi-directional power flows, dynamic grid configurations, and we also will have evolving business and market structures. So this is what the future grid needs to look like, and this is what we're doing to get from where we are today to where we need to be. So on the vertical trajectory that I had on the previous slide, to support the bulk system, one of the big challenges is we need to increase transmission capacity. We need to expand transmission. And increasing transmission capacity does not necessarily mean building a lot of new transmission, which we need to do as well. We need to build new transmission, but we have a lot of untapped resources in the existing right-of-ways. So we're developing technologies that can support increasing capacity for the existing transmission lines, like grid-enhancing technologies, including dynamic line rating, power flow controllers, topology control algorithms, advanced conductors, and high voltage direct current. So HVDC is one of the big efforts that we're pursuing. It's very expensive, it's not cheap, and not gonna happen overnight, but there is a lot of support for this initiative. So in fact, the Congress in FY23 budget put a specific language encouraging us to create HVDC moonshot to support research and development, to reduce cost and improve performance for technology that can support long distance transmission. On the distribution side, going to the horizontal direction is we really need to enable seamless integration, and the flexibility is very critical. So it's crucial for all these resources to be smoothly integrated into the grid. So the grid architecture should be able to accommodate all these distributed systems. And as I mentioned, as line between transmission and distribution are blurring more and more, we need to have different designs, different planning, different operation mechanisms. And also linkage between energy management system that used to control your bulk operations and distribution management system that is controlling your distribution components, it becoming more and more important. So we're moving from tens or hundreds of thousands of devices that we have on transmission and distribution system and generation. So to transmission system with tens of millions of devices, and it includes customers, includes homes. So we need to have better modeling, we need to have better controls, we need to have new mechanisms how to operate all these tens of millions control points, which brings a lot of challenges starting with cybersecurity, fast computational capabilities, and big data management, which requires artificial intelligence and other advanced tools. One of the tools in our portfolio is microgrids. So microgrids traditionally were used to support local resilience and help with more efficient integration of renewable energy resources. But the way we envision future microgrid is a building block of the larger grid. In fact, we look at the future grid as being fractal. So when you start with single solar panel, then you aggregate it in microgrid, then you aggregate entire feeder, substation, and then it supports the operation of the whole system. And with FERC 2222, which is a ruling from FERC that allows for aggregated resources on distribution side to support transmission system, bulk system, we're going to see a lot more participation from the customers. You need to make sure that this participation can be enabled, but it has to be responsible participation. So that requires us to have a lot of computational capabilities, a lot of communication systems, and all of this needs to be secure. So those are the things we're working on as well. And when you develop all these new systems, as we probably all know, for those of us who've been in the industry for many years, utility industry is not necessarily big risk takers. They're very risk adverse. So we need to help the industry to adopt these new technologies to accelerate the adoption in the marketplace. And if you go through this, what they call TRL, technology readiness level, as you develop new technology, there are several things that we call valleys of death. So what we are focusing at our office is on the two valleys of death that you see on the slide. So the commercialization valley of death and profitability valley of death. What is happening is when technologies get developed, you don't know how it will perform in real life. And sometimes utilities don't want to take the risk to deploy it in the live system to see if it will perform the way it is promised by the vendor, or it will deliver the economic benefits that they expect. So we have a new program that started in the FY23. We call it AGTS, Applied Grid Transformation Solutions. An idea for this program is to take this new technology and deploy it in the control pilot environment. It can be at a national lab or at the utility test platform if they want to participate, private industry. But the idea is to validate techno-social-economic performance of this new technology. So when industry wants to adopt it, they know what to expect. They see the results, so we can use simulated environments in addition to a real environment. We use hardware in the loop. We use different analytical tools to understand what the economic value, if it can meet all the performance and functional requirements, and then we can share the results with the industry, and we expect that this will help to accelerate adoption for new technologies in the years to come. And while I'm talking about technology, I really want to emphasize that as much as I'm excited being a former engineer to talk about technology, technology by itself cannot succeed. We need to have markets that can support adoption of this technology. And for markets to exist, we need to have right policies. So we are working with stakeholders, providing technical assistance to utility commissions to make sure that the right policies are adopted that can create the markets that can support adoption and deployment of this new technology. So we really need coordinated strategy, and this is what department is focused on. This is the value we see that we can bring to the industry, but we can't do it alone. So we really need support from all of you. So more engagement we see, more information we get from the industry, the easier for us to do our job and the more value we can bring to the industry. So this is, I think, all I want to talk about today. So thank you very much for your time. And I don't know if you have time for questions, but thank you.